Good morning. And now in the next few lectures, maybe 5 lectures or so, we will be discussing about the solubility of the non-homogeneous equation with a homogeneous boundary condition. And what we use is what is called the Newtonian potential, and this is also known as the potential theory. So before coming to the potential theory, let me spend some 10-15 minutes, maybe 10 minutes of what we done last year and some few examples we left out in the previous class about the Perone's method. So in the Perone's method, Perone, we were studying this problem, plus n of u equal to 0 in omega and u equal to g on d omega, and you will see that solubility is equivalent to some regularity of d omega. Okay, but then this regularity may not be, it's basically an existence of sign negative subharmonic function. Okay, somewhat. So today we will give two examples where you can verify this regularity. So example 1 is we need some sufficient conditions to verify that. Example 1, this is the case when n equal to 2. That's a pretty little bit easy. So you have a domain here in n equal to 2 omega subset of her, and then you take a point z belongs to, so yeah, I'm writing it in this format, z naught belongs to d omega. So it will be of xy form, and you, without loss of generality, so you have a point z naught here, and without loss of generality you take that to be 0. Okay, so you can take that, doesn't matter without loss of, because you can shift the domain if you like it. Okay, without loss of generality you take z naught equal to 0, and suppose n is a neighborhood of z naught, and look at, this is the neighborhood, so you have it a neighborhood of n, and look at this part, that is an intersection omega, and then neighborhood of z naught, and then you use the polar coordinates r theta. So I will define the expansion polar coordinates r theta, and because theta is the angle, it can have multiple value, so we take the single valued branch of single, so assume that is possible. Okay, single valued branch of theta, so the boundary is such that you can choose this theta as a single valued branch defined on omega intersection n, So I will exactly define you the thing, then you verify. So I am not going to verify here, verify that in complex format. I am writing it as z, verify that so I define wz is equal to, for z in that, minus real part of, that's why you are taking single value, logarithm of z, that's nothing but, you can compute this is nothing but log r. So I'm taking already normalized with z equal to 0, this is log square r, you can compute this, plus theta square, where z not equal to 0. So for z not equal to 0, and z is like a complex number, so on the complex notation I am giving, and define w at 0 is equal to limit z tends to 0, that limit exists. Okay, limit z tends to 0 of wz at that limit. Then you can verify that W is a barrier. That's what you have to verify regularity. Okay, it's a barrier at z not equal to 0. That's what you want to prove regularity. So whenever you have the single valued branch and every neighborhood, you can do that one. So geometrically it says that so the boundary value problem in a plane, that's what you have in a plane domain. Okay, n equal to 2 is always solvable okay, if we can access, if the boundary point, if the boundary points are accessible from exterior of omega, by a simple arc. So whenever you can, so the R2 more or less it's easy to solve in a domain, but when example 2, but when you go to higher dimensions, example 2, in higher dimensions things are not that simple. One sufficient condition, higher dimensions, it's not simple. It's more delicate. It is more delicate. For example, if you have a domain like this, if you have a sharp something like domain in n greater than or equal to 3, solubility is an issue in such kind of domains. So one condition of regularity is what is called an exterior sphere condition. Exterior sphere condition. This is much stronger. So exterior sphere condition is satisfied, then exterior sphere condition implies regularity. So this is a more regular. So as I said, there are various ways of defining regular exterior uniform sphere condition. Basically this one, regular. Okay, so what is this exterior sphere condition? Geometrically it means that if you have a domain, you can attach a sphere at all points of the uniform radius. That's it, attach. So you may not be able to do that. For example, you cannot attach a sphere here at all, which is exterior. Okay, so it should be uniform sphere condition. Okay, so you will be able to attach a sphere. That means exterior sphere condition means their axes are positive, such that for all psi on d omega, you look at the ball of radius r, and then you take its closure. So it touches at the closure. Intersection omega bar is this singleton. Okay. That means only at this point psi you can put this ball, and this ball is uniform. R works for everywhere. So in this case, okay, in this case you can define, so then define W of x equal to, with this condition, so you can prove all these, r power 2 minus n, this is n greater than or equal to 3, minus modulus of x minus I power 2 minus n when n greater than or equal to 3. Okay, any condition you can define. This is another way of giving the condition. This is more stronger condition. X minus I by R when n equal to 2 is a barrier at psi. That means that implies omega is regular. Okay. All right. So with these two conditions, I will move on to my next Newtonian potential. Maybe we'll start with a new page. So we will go to the potential theory now. Potential theory. Okay, so we'll go a little bit slowly. So what to do? So let's see. So let me give you a brief idea about what we are going to do. So we need to solve the homogeneous equation. We need to solve the inhomogeneous equation. Minus Laplacian of u equal to f in omega and u equal to 0 on boundary. And you know that from the representation formula, if u solves, then the representation formula tells you u of x is equal to, using the Green's function, g of x minus y f of y dy. This is on omega, and there won't be the second term on the boundary which thing that, and g is the Green's function. G is the Green's function. And right now we are, because we have already done by Perone's method, we have done by Perone, we have done the boundary analysis by Perone's method. Boundary analysis by Perone's method. So we will not worry about the boundary condition now. So the difference between your Green's function and g is only that g take care of the boundary condition also. But g and phi, the fundamental solution phi have the same singularity. And the singularity is the one it is recovering your source term. So far you have seen the earlier lectures on PDE1 and other things. You can see that singularity of that is what eventually recovers your f, the source term. Have the same singularity. That's what we have, same singularity. Because we don't impose any boundary condition on the fundamental solution. On the other hand, G satisfies the zero boundary condition, which you have seen it. Okay, so have that. Thus, we consider this. Thus, it's enough to consider. So we don't worry about the boundary now. So we consider the integral. Vx equal to, with respect to the phi of x minus y, f of y. F is given to you. We will talk about more about it. This is over omega. Okay. So you have your domain omega. So we will talk about. So we want to understand this boundary condition. Okay. So you want to. So and this is called this integral. is called the Newtonian potential. Okay. Newtonian potential. Okay. So what is so solvability basically? So solvability reduces to that of deriving. So that's what, because this is singularity for phi, reduces to that of deriving estimates on V. Estimates on V. You will see that in the next few lectures, and its derivatives. That is, and its derivatives. Okay. So the Newtonian potential, one of the major thing is that Newtonian potential need not be twice differentiable. That's the trouble. So the issue, the question, the difficulty is here. Newtonian potential need not be twice differentiable. So that's the issue, because if you want to compute your Laplacian of phi, you have to take that Laplacian inside the integral. But then phi and its derivatives are locally integrable, but d phi by d square. So the problems are that phi d phi by d psi, you have seen this in the PDE1 course, are locally integrable. But that's where the problem. But d square phi by dxi dxj is not locally integrable. So you cannot take the differentiation under the integral sign, not locally integrable. You see, the trouble comes there. So this involves regularization of phi. This involves regularization of phi appropriately. So what we will do a very little analysis. We will not do it. If you want more detailed analysis, just refer the Gilbert Gardner. As I said earlier, it's a complete analysis on elliptic equations, not only potential theory, a lot of analysis there in the Gilbert Rudiger book about the Schauder theory also. So you can, if you want to have master these things, you can refer this book. Okay. So now another remark which you want to make it here, remark. This is where the troubles now issues. When U is C2 of omega, when U belongs to, before proceeding, let me tell why we want the difficulties in studying Newtonian potentials. When U equal to 0, C2, then this immediately implies my Laplacian U. In fact, minus or plus doesn't matter. Suppose you take minus or minus. F. This is a continuous function, right? So whenever you have a U is a C2 function which is termed with the classical solutions which we look, then Laplacian U equal to. So it is natural to look for solubility. This is given you think. So naturally when F is continuous, you expect to have solution U in C2. So it is natural to look for solutions Look for solutions. Solution of the minus Laplacian of u equal to f with continuous f. See, with continuous f. But the unfortunate issue is that when f is but, this is not the case. This is not the case. In other words, f continuous may not produce, may not imply solubility, classical solubility. We will give an example. Classical it does not imply classical solubility. You see, so there is some trouble. So if we say, we'll give an example. Okay, so you see, so you have trouble. But when f is, suppose you have f is c1 of omega bar, then solubility is not difficult. Then solubility, we will do this also. Solubility is easy to establish. But this is a very strong condition now. So you are assuming a C1ness of that. It's a strong condition. We want to get rid of that. We don't want to. So just strong condition. So you see. So when f is continuous, need not be thing. So you have continuity which is quite weaker, and but when it is C1, you have the solubility, but it's a strong condition. So what we are going to do that we want to weaker condition. So we want to introduce a space X such that it is smaller than continuity C0 but bigger than C1. Okay, so that the problem is solvable for all f in X. You see, so you don't have solubility here in general. You have solubility here, but you want, and this turned out to be what I call a Helder continuous functions. We will introduce in the process Helder continuous functions. We will introduce in the next lecture. Continuous function space, continuous functions and space you define, and hence requires a finer analysis. You don't have requires a finer analysis because you don't have the differentiability, so you cannot do easily the integration under the integrals because you can't differentiate f anymore. Okay, requires a finer analysis. So if you recall the PDE1 codes, when f is in C2 and compact support, you have seen you can get the solution by differentiating f. If you go back and see that analysis, and so we'll start with a proposition now. First a proposition. Okay. So this is something different. First you need first a proposition. So I may not be able to prove it here, so maybe I will prove it in the next class. So let me at least try to give a proof. At least let me try to explain to you what it is, and then we will continue this one. Okay, so let me write a proposition. Okay, what is called a proposition? What is called the removable singularity. So I'll explain this, and then maybe we'll give a proof in the removable singularity. So first understand that one, and then the proof will be given here. Okay, suppose omega is an open set in Rn. And x naught belongs to omega, comma, and u is a harmonic function in omega minus x naught. So x naught is a possible singularity of u. So that is what we have to get. Okay. So c naught u is a harmonic function in omega. So you can have a singularity, but then I don't want a singularity. That's what very delicate issue. Don't want a singularity which is worse than my fundamental solution singularity. I'll explain a little bit here, and then we will proceed here. Okay. So assume the singular. I will explain that. Assume the singularity, if at all singularity. If you have no singularity, no issue. But if at all there is a singularity, so the singularity of u of x should be something like a small order of, that's a meaning of small order of x minus x naught. Okay, so singularity. Okay, as x tends to x naught. So the singularity, we don't want a strong singularity than my fundamental solution, where phi is a fundamental solution to my Laplacian. Okay, phi is the fundamental solution of minus Laplacian. Okay, then if the singularity is more, essentially it says that you cannot have a singularity, or you can remove the singularity basically. So you're not given there is a singularity or not. If the singularity is less than that, you can remove that singularity. Then you can be suitably define at x naught, so that u becomes harmonic in omega. So let me explain a little more about the thing. So this is we will prove this in next class. Okay, we will give a proof of this one. So, but what does this mean? So if you look at it, phi of x minus x naught, say you take n equal to 3, for example, then the singularity is something like 1 over mod x minus x naught. That's a singularity. So if this power increases here, so for example 1 by x minus x naught whole square is strong singularity, then that's it, right? It is strong, it goes much faster to infinity. Okay. Strong singularity, then phi. On the other hand, if you take 1 over mod x minus x naught power say half, then it is a weaker singularity than then phi. So if I define u1 here, u2 here, then you can see that u1 is u2 is smaller order of phi of x minus x naught. Because if you look at it here, if I take u2 by phi, so you see, and you will have something like this, mod x minus x naught. This comes at the top, singularity, by mod x minus x naught half, and this goes to 0. So that's what you want to show, that as x tends to x naught. You see, so it is a small order of that. So you have to understand the small order, and u2 by that function should go to 0 as x tends to x naught. So that's what. So if you have, and this is assumptions, need not be in this form. It can be, the singularities can come in different form and different functions. But it's basically that the singularity cannot be that strong. It should be in order. It should be strictly less than the normal singularity. And that's what we want to do it. So if that is the case, so it's essentially said that if you have a harmonic function in except one point, and its singularity is in order smaller than small order of this singularity, or smaller, doesn't matter, it goes to 0, and then that singularity essentially can be removed. That means you don't have really singularity. It's a removable singularity which you can do it. We use this concept to prove something. First of all, in the next class we will prove that this removable singularity theorem. So we will stop at this stage now, and then we will continue in the next lecture. Thank you.